Welcome to This Explainer. We're jumping straight in today to completely strip away the sci-fi mystique of artificial intelligence. Look, we aren't going to talk about magic brains or sentient robots here. Instead, we're going to look at AI for what it actually is. It's a massive, tangible, mathematical assembly line. All right, let's dive right into this. Here's our agenda for the assembly line today. 1. The raw material, which is data. 2. The engine, our AI models. 3. The process, or training. 4. The types of AI learning. And finally, 5. The limits of AI. Starting off with Section 1, the raw material, data. To really get this, think of an AI kind of like a child who only knows exactly what they've seen and heard, nothing more. It has absolutely zero innate knowledge. It doesn't inherently know what a cat is, or how to speak English, or even what the sky looks like. Every single fact it knows, every pattern it spots, every skill it has, it all has to come directly from the examples it gets fed. Simply put, without data, there is no learning. Period. And because it relies so heavily on what it's fed, the absolute golden rule of this whole factory is garbage in, garbage out. Quality matters way more than quantity here. If you train a model on incomplete or just straight up incorrect data, it's going to learn the wrong patterns. In fact, cleaning and curating properly labeled data, that's about 80% of the real work in AI development. But while quality is definitely vital, the true magic is the staggering scale. We are not talking about feeding the AI a couple of textbooks. Large language models like GPT or Claude consume hundreds of billions to literally trillions of words. That's essentially a huge fraction of all human text ever written. It is the equivalent of a system reading millions of books before it even tries to answer a single question. It does all this to extract these deeply hidden statistical patterns, relationships between words, rules of grammar, that eventually allow it to generalize to totally new, unseen inputs. Moving on to Section 2, the engine, AI models. Once we've got our absolute mountain of data, we move to the engine itself. At its core, an AI is not a biological brain. It is a giant mathematical function. Input goes in, output comes out. And its absolute most important ingredient is a parameter. You can think of the AI model as an incredibly complex recipe, right? Well, parameters are the countless tiny dials or ingredients that we tweak over and over until the recipe tastes perfectly right. They're the actual learnable parts of the network. Just to give you a sense of the sheer, mind-bending scale of these engines, GPT-4 is estimated to have roughly 1.8 trillion of these parameters. And you know what the craziest part is? Before training even begins, all of those dials are set completely at random. The model's initial output is quite literally just random noise. The entire process of AI development is slowly, painstakingly turning that random noise into intelligence. It happens one tiny mathematical adjustment at a time, across billions of connections that are very loosely inspired by the layers of a human brain. Which brings us to Section 3, the process, training. So how in the world do we actually tune trillions of dials? How do we go from random, useless noise to a system that can instantly write code or generate poetry? Well, training is fundamentally a massive feedback loop, and it's repeated billions of times. First, the model makes a prediction. Then it compares that prediction to the actual correct answer. The difference between those two things is the error, which we track on something called a loss curve. Finally, the model adjusts its parameters to reduce that error for the next time. Ultimately, we want to see that loss curve falling steadily over time. This actually perfectly illustrates the raw mechanics of learning. It is exactly like a person learning to shoot hoops. The AI takes a shot. It measures exactly how far off it was from the basket. It makes a microscopic adjustment to its technique, and then it shoots again, over and over and over. Behind the scenes, the math making all of this happen is super fascinating. When the AI misses that basketball shot, a process called backpropagation works backward through the network to distribute the blame. It calculates exactly how much each specific parameter contributed to that miss. Then, an algorithm called gradient descent mathematically calculates the precise direction to move each dial to fix it. Think of it like a physical 3D landscape of errors. The entire goal of gradient descent is just to roll a ball down a hill to the very lowest point of that valley. That lowest point represents the lowest possible error rate. Now, doing this requires an astronomical amount of compute power. We're talking tens of millions of dollars and months of time running on thousands of highly specialized chips. All right, Section 4, Types of AI Learning. Once the basic engine is humming along and we know how to tune those dials, there are three main ways we can train these models. In supervised learning, the AI learns from a strict teacher who provides all the correct labels, like actively teaching it what a cat looks like. Then there's unsupervised learning. Here, there are no labels. The AI just discovers hidden structures entirely on its own. It's like sorting a massive pile of foreign coins purely by their shape and color without knowing anything about the currency. And finally, reinforcement learning. This is literally like training a dog with treats. The model takes actions and gets either rewards or penalties to modify its behavior. This is actually exactly how models like ChatGPT are fine-tuned to be helpful and safe based on human feedback. Now, let's look at a concept that absolutely changed the game. While traditional deep learning uses many layers to build complex patterns, a massive breakthrough architecture was introduced back in 2017 called the transformer. It is a foundation of all modern large language models. And its biggest innovation? A mechanism called attention. To process text, an AI turns words into lists of numbers called embeddings. Think of these as GPS coordinates for meaning, where similar concepts live in the exact same mathematical neighborhood. What attention does is allow every single word in a sentence to constantly ask every other word, hey, are you relevant to me? It weighs the context of literally everything that came before it. This is exactly why a modern AI can handle incredibly long, highly complex paragraphs without forgetting the context of the very first sentence it read. Which brings us to our final part, Section 5, the limits of AI. So, we've built the engine, we've trained it, we've given it specialized skills. But to really understand our factory's final product, we have to talk about its critical limitations. And this brings up the million-dollar question. When an AI produces a brilliant essay, or writes flawless code, or diagnoses a medical symptom perfectly, does it actually comprehend what it's saying to you? The crucial takeaway here is no. It really doesn't. AI does not know facts the way a human being does. It is merely predicting the most statistically likely next token or word based on its massive training data. It is essentially a very, very well-read parrot. And this is exactly why AI can hallucinate, producing incredibly fluent, highly confident, yet completely fabricated and wrong answers. It's just predicting what should come next. It's not actually verifying the truth. On top of that, most deployed models suffer from a lack of continuous learning. They're totally static. Once the training stops, the learning stops. They act a lot like a doctor who finished medical school years ago and never learns a single new thing from any of the patients they see today. Updating an AI without it completely forgetting what it already knows, a problem known as catastrophic forgetting, remains a major, unsolved challenge in the field right now. Ultimately, as we wrap up this explainer, I really want you to remember this. An AI is just billions of tiny mathematical knobs being adjusted by a very simple, repetitive feedback loop. It's a mechanical, statistical process. It only feels like magic because of the totally incomprehensible scale of the data and the computing power involved. We're talking trillions of words, trillions of parameters, billions of micro-adjustments. But if intelligence can be simulated this convincingly just by scaling up a massive statistical guessing game, what does that actually say about how our own biological brains really work?